Hello, everyone. Thank you for the introduction. Welcome to this talk. And my name is Hao Sun. I'm currently a first-year PhD at ETH Zurich, working with Professor Zhendong. And in this work, we aim to produce a very simple but effective approach to validate a program verifier. And we demonstrate our idea in the eBPF verifier, which is a critical component in the Linux kernel. And so since we are in a verification section, let's now motivate this problem from this perspective. So most of us believe that a verified program is correct with respect to its specification, right? Because a verifier considers all possible program state or each potential execution path, and it's strictly reason about the program, right? Positive verification, therefore, should likely implies the correctness of the verifier. So do you think this statement is true or false, that a verified program is correct with respect to its specification? Well, it's not actually true. The fact is that a verified program is correct only if the corresponding verification is solved. More specifically, the verifier should correctly abstract program state, and the techniques it relies on, such as the SPT solver, should also be solved. Otherwise, the conclusion is unreliable. And what's even worse is that the confidence given by a potentially unsolved verifier is very dangerous. So imagine that you strongly believe a program is correct because you think it's verified. So you execute it everywhere, even in your kernel. But in fact, there are some incorrectness issues, but they are missed by your verifier. So the problem here is that we try to give a very strong guarantee by using verification. But who gives the confidence that your verification is correct? So one possible solution to this is using proof, right? Let's not trust the verifier. Let's make it to produce a proof where the verifier concludes the program is safe. So in this way, we don't need to trust anything. All we need to do is to validate this proof by ourselves. But the problem here is that a proof is not always available. For example, most verifiers do not have very good support for proof mode. And the eBPF verifier is based on abstract interpretation. It does not support any proof mode, and adding such support is non-trivial. Furthermore, even if we have a proof, all it shows is some conditions hold. But how do we know those proved conditions are consistent with their specification? So you may propose, okay, let's also verify the verifier with another verifier. So the same question again, why should I trust your verifier? You have proof, or it's verified by another verifier? So I can ask the same question recursively. So essentially, we don't have a minimal trust base here to bootstrap all the trust chain. And furthermore, if we try to apply proof-based or verification-based approach to provide a strong guarantee into our verification, it will require huge effort because it requires huge domain knowledge to specify the specification, and the code base of verifier is normally very huge and complex, and they change very frequently. So the problem here, how can we provide stronger guarantee to our verifier? So with that said, in this work, we try to explore a new approach, and we try to use a simple, not proof-based, not verification-based, but simply validate with some high-level variant. And more interestingly, we try to validate the verifier by the verifier itself. So our focus in this work is in the eBPF verifier. So here is a bit more information related to this technique. So eBPF enables user space process to dynamically extend the kernel with third-party extensions. A verifier is in place to validate the safety of those extensions. The eBPF verifier validates program using an abstract interpretation-based technique and tracking program state in different abstract domains, such as interval domains, trace state domains, and only programs deemed safe by it can be loaded. So therefore, you can imagine incorrect verification in this context may cause significant consequences because it may lead to potential malicious intentions to be loaded. And The verifier now is one of the most complicated components of the eBPF subsystem. So how do we validate such a component without using proof or verify it? So we use a different approach. So we know that most verifiers reason about program, abstract program state. In the context of eBPF verifier, it approximates program state with different abstract domains. The checking process of the eBPF verifier can be essentially viewed as an approximation tree, as shown in the figure here. And each path in this tree corresponds to an execution path. And approximation at each node corresponds to a set of concrete states at that specific location. So a very important invariant here is that each approximation must correctly over-approximate all possible concrete state, not other approximation. So otherwise, the safety of executions with non-complete state is unknown, and they can be potentially exploited. So this tells us we can utilize this invariant to validate and test the verifier. But the problem is, how do we do this? How do we validate this property? So we know verifier reason about program. And our goal here is to validate some property. So why not let the verifier validate this property? Why not let the verifier validate itself? So, such as we don't need to do anything, right? We don't need to care about its internal workflow. So therefore, we propose state embedding, an automatic technique to detect unsoundness issues in a program verifier. So the key workflow here, as shown in the slide, we have 3 essential steps. So for each accepted program P, we execute it at profile concrete states, which build our ground truth. And then we follow those states to achieve effective validation, which I will talk later. And finally, we transform the program by embedding profile states in some program construct, such that we are taking as input the state embedded program, the verifier automatically validates if those states are contained. So with our approach, we essentially compare pairs of program, P and P prime, where P is a safe program accepted by the verifier, and P prime is a transformed state embedded program. And the invariant here is that for this accepted program P, a sound verifier should reject this P prime. Otherwise, we have further unsoundness issue, right? So the first step, as I mentioned, is to profile concrete state. So here we have generated program and we execute and trace it so that we can collect runtime state at each basic block level, as shown in the slides. So those states are profiled from real execution. So we know they must be contained within corresponding approximation. So we therefore have ground truth here. So for the example, in the left part, we can see during execution, the program jumps from the third instruction to the last one. And here, we collected 2 values for R1 and R2, and we know R1 equals -1 and R2 equals 1 must be contained in the approximation, and we need to validate this. So how do we validate this? And we embed those states into certain constructs. And the semantic of those constructs essentially is something like this condition statement. So it directs the verifier to validate if the profile state is contained. So let's say this example here. So at each basic block, we collected different concrete state, and then we use 2 instructions, like the 8 and the 9 instruction. When the verifier interprets this construct, it checks if the value, if R9 could equal to -1. Essentially, it checks if -1 is contained in its approximation. If so, the sink will be detected because this path will be non-taken, so the non-taken path. So the sink will be reported. And this is the indicator that concrete state is contained. Otherwise, it jumps the sink from jumps instruction 9 to instruction 10, and we know there is an issue. So this is what we call embedding. So in practice, concrete could be, we can collect a lot of concrete states, which means we may need to insert a lot of conditional statements in a source program. So this may lead a lot of redundant checks because the verifier may fork export passes at every conditional statement. And to avoid this, we use folding. So the idea is just to we allocate a global state and we fold and reduce all the profile state into this global state. And eventually, we only embed the folded state once. So as shown in the example here, so first we reserve R9 and initialize it. And then when the program jumps from the fourth instruction to the sixth instruction, we insert arithmetic instructions to fold R1 and R9 into R2 into R9. So during this process, we can calculate the value of R9, which is -1 in this case. And then we embed the concrete state of R9 only once. So that's all about state embedding. So in summary, we only need 3 steps: profiling, so that we have ground truth; folding, so that we reduce needed checks; and finally, embed once. And then the verifier checks itself. We don't need to do anything else. So does this work? Yes, we have found 15 previous unknown bugs in the eBPF verifier. And most importantly, many of them are very critical. And 2 of them are exploitable, which I can use to achieve local privilege escalation. And I think many bugs, I just checked yesterday, many bugs are fixed. Only 1 is left, it's still being discussed. So as shown in the slides, a bug we reported requires significant change to the eBPF verifier. So here we added more than 300 lines of code just to fix this bug. And we also find other interesting bugs like this one. This is a bug that I can exploit to achieve local privilege escalation. And as you can see, the root cause of this critical bug is very simple, right? It just incorrect typecast as shown in the patch. But it's very tricky. It's missed by experienced maintainers. And after figuring this out, I fixed the bug, and all the patch has been backported to a previous stable release. And here is how we exploit it. So the left part is just example we mentioned before, and the right part is how we exploit it. So essentially, at the 6th instruction, the verifier lost range of R1. The size information is lost. So here at instruction 3, we just do a shift and we do an add, and then the verifier thinks the value of R1 equals to 0. But at runtime, its value is 1. So with this basic register value, we can achieve various operations. For example, here we multiply it and use this as a last parameter and invoke a helper function to load some user space data to kernel space. Since the length is controlled by us, we can overwrite the stack memory and then obtain an arbitrary pointer from user space. So that's why we can exploit this bug. So the point here is that these bugs are very critical and we need to fix them immediately. And so, furthermore, we can find bugs in different components. As shown in the table, we found 6 bugs in range analysis. We can also find bugs in memory access, state pool, and control flow graph check. So the reason is because we use a pretty high-level invert here. So all the incorrectness issues in those procedures can be propagated to range analysis and thereby discovered by us. And here are more examples. And you can refer to our paper for more details. So thank you for your attention.